Sesim geliyor mu? Sesim geliyor mu?
Geliyor hocam, bir problem yok.
Tamam. Okay. Evet arkadaşlar, geçen haftaki vize sınavı nasıldı? Kolay mıydı, zor muydu? Yorum yok mu? Evet arkadaşlar, önceki hafta ne yapmıştık? Fourier serilerini işlemiştik. Bu arada dersten önce benim bu OneNote için kullandığım, tablet için kullandığım elektronik kalemim bozuldu. Dolayısıyla önceki derslerdeki gibi yazamayacağım. Geçen seneki notlar üzerinden anlatacağım bu hafta. Tamam mı arkadaşlar?
Geçmiş olsun hocam.
Sağ olsun. Ucunda küçücük bir böyle kalem ucu gibi siyah bir şey var. Bir baktım düşmüş ama nereye düşmüş bilmiyorum. Bulamadım. Yeni bir kalem almak lazım o zaman.
Hocam o vakum ise ya da vakum tarzında bir şey, onu o ucu sadece o ucu sipariş edebilirsiniz.
Öyle mi?
Evet, benim bir arkadaşım vakum kullanıyor.
Yok, ben şey kullanıyorum. Surface. Microsoft Surface.
Surface'i bilmiyorum ama onun farklı ucular var. Hatta bazılar işte farklı tactile feel veriyorlar.
Anladım.
Sadece orada uçları veriyor. Belki Microsoft'un aynı bir şey olabilir.
Evet, manyetik bir şey. Böyle küçücük bir şey ama düşmüş. Bir bakayım internetten. Neyse, bu haftalık arkadaşlar geçen seneki aynı notlardan devam edeceğiz. Okay. Şimdi ben screen'i görüyorsunuz değil mi arkadaşlar? Can you see my screen?
Yes, we can.
Okay. Bir de başlamadan önce gelecek hafta biliyorsunuz çarşamba öğleden sonra Arefe bayram olduğu için haftaya dersimiz olmayacak maalesef. Şimdiden bilgilendireyim. Unutursam şimdiden size iyi bayramlar diliyorum. Hayırlı bayramlar.
Size de hocam.
Size de iyi bayramlar hocam.
Okay, so in the previous lecture we learned about the Fourier series, and we know that the Fourier series only can be applied to the periodic signals. Remember, we give you the condition for a signal to be a periodic or non-periodic. So the Fourier series can be applied only to periodic signals. However, you know, most of the signals in practice that we use in our daily life, like a radar signal or medical signal or audio signal, video signal, and so on, can be mostly they're non-periodic signals. So therefore, we cannot apply Fourier series. Instead, we apply Fourier transform to such non-periodic signals. That's why today we are going to learn another type of Fourier, which is called Fourier transform. And this is one of the most popular transform that we used in many engineering fields, in electronics, in computer, in medicine, in radar, you know, and in many technology, we use this Fourier transform. So that's why Fourier transform is very important. So, okay, so let's start with the Fourier transform. Can you see my cursor?
Yes, we can.
Okay, so Fourier transform can be applied to the non-periodic signals. That's what we said before. So I'm going to give you first a Fourier transform, which is forward Fourier transform. It transforms your signal f of t in the time domain to the frequency domain, or some people they call W domain. And we have the reverse operation, which we call inverse Fourier transform, is to transform a signal in frequency domain back to the time domain. So that's what is called inverse Fourier transform. So let's start first with forward Fourier transform, which is equal to, as you see, f of t is equal to f of w, which is given as follows: from minus infinity to infinity, the integration f of t times exponential minus j omega t dt. So this way we convert a signal from a time domain to a frequency domain using the Fourier transform. So after we transform a signal to frequency domain, we can represent in different form. But one of the most popular form is called polar form. Polar form is given as follows: f of w is equal to the magnitude, which is absolute value of the f of w, times exponential j angle information. So this form is called polar form that we may use sometimes. So that's the equation for the forward Fourier transform. For the inverse Fourier transform, we have this equation f of minus 1, so which is going to end up with f of t, and that's equal to 1 over 2 pi integration from minus infinity to infinity f of w times exponential j omega t dw. So the main difference between forward and the inverse Fourier transform, as you see, in the forward one, we have an exponential minus j omega t. In the inverse Fourier transform, we have the positive of that, which is plus j omega t exponential. So that's one of the main difference between the forward and the inverse Fourier transform. So after giving this definition, let's start with some example, which is given as follows. F of t is equal to exponential minus at times unit step function, which is u of t. So that's our signal in time domain, right? And the question is, can you convert this signal to frequency domain using the Fourier transform? So basically, what's the Fourier transform of this signal? That's our question. Okay, let's solve it together. F of w is equal to, from minus infinity to infinity, that's our definition, right? F of t, our signal in time domain, times exponential minus j omega t dt. That's what just we got from the definition above. So what I'm gonna do is just replace the f of t with the given signal. So this f of t I'm gonna replace with the exponential minus at times u of t, our unit step function, times exponential minus j omega t dt. So the rest is to solve this integration, which consists of multiplication of two exponential signal. So since since both are exponential, I can combine their power, right? Under one single exponential function, which is here, integration from minus infinity to infinity, exponential minus a plus j omega t, a plus j omega times t dt. So you guys know how to solve this integration from your maybe high school or previous math background. So let's solve it together, which is equal to 1 over minus a plus j omega times exponential minus a plus j omega times t. And the upper limit is going to start from 0 because of the unit step function. Unit step function, remember guys, it was equal to 0 from minus infinity to up to 0, and then from 0 to the infinity it was equal to 1. That's why we put 1 there and we changed the lower limit from minus infinity to 0. Now we are going to evaluate this result for this upper and lower limit. So if you put this plug into the equation, you're going to end up with this result, which is the Fourier transform of the signal that I gave you above. So the result is f of w is equal to 1 over a plus j omega, and the a is greater than 0. So that's the Fourier transform of such a signal, which is exponential minus at times u of t. So if you transform the signal to frequency domain, you're going to end up with such signal. And remember guys, we learned a polar form. Let's convert this result and represent this result in terms of polar form, which was magnitude times exponential angle information. And the magnitude, how do we obtain, is equal to this 1 over square root of a square plus omega square times exponential minus j arctangent w over a. So I may ask you guys to convert this result into the polar form. So this is how you are going to convert into polar form. As a result,
tables like Z transforms, for example.
can you repeat your question, please?
Are there tables like for Z transforms?
Yes, exactly. So you're gonna check this result in the table in your textbook. I guess it was table 7.1. Okay, so we have the predefined pairs in that table for the Fourier transform, similar to the Z and Laplace transform. But you should know how these results are obtained in that table.
Yes, of
okay.
course.
So that's one of the most popular or most common signal that we use in that table that your friend mentioned. Okay, that's one of the example how to convert a signal from time domain to frequency domain using the Fourier transform. Okay, the next topic is about the linearity of Fourier transform. This is very critical. So in terms of, analysis of a system. So the question is, the Fourier transform is linear or not? Yes, it's a linear operation. So let's look at it together. Fourier transform is linear if it satisfies this superposition condition. Remember, guys, at the beginning of the semester that we learned. Assume that we have a time domain signal f1 of t, which has a Fourier transform of f1 of w. Similarly, assume that we have second signal, which is f2 of t. The corresponding Fourier transform is f2 of w. Then, if you apply the superposition condition to these two signals, which is a1 times f1 of t plus a2 times f2 of t, if the corresponding Fourier transform is in the similar form, which is a1 times f1 of w plus a2 times f2 of w. Okay, and then you'll see that it satisfies this condition, that I'm skipping the detail here. So in summary, yes, the Fourier transform is a linear operation. Okay, the next question is, we have learned many different transforms, such as the Laplace transform, Z transform, and then Fourier transform. There are connections between these different transforms. For instance, in our case, there's a connection between the Fourier transform and the Laplace transform. So let's write down the Fourier transform. Remember, guys, it was Fw was equal to, from minus infinity to infinity, f of t times exponential minus j omega t dt. And remember, guys, the Laplace transform equation was f of s was equal to, from minus infinity to infinity, f of t times exponential minus st dt. In this case, if you guys remember, s was equal to sigma plus j omega. So if sigma, if the sigma is equal to 0, then the Laplace transform reduced down to the Fourier transform. In other words, Fourier transform is a special case of Laplace transform when the sigma is equal to 0. So Fourier transform is a special case of a subset of Laplace transform when the sigma is equal to 0. In other words, when the s is equal to j omega. So there's a such connection between Fourier transform and the Laplace transform. Any questions so far? Okay. Then let's continue with more example to understand this transform further in details. So Fourier transform of some useful functions. Let's start with one of the most common function that we used in many engineering system, which is called rectangular, or some people they call square signal, because the shape, as you see, looks like a square, right? Sorry, rectangular. Sorry about that. So mathematically is defined as follows: f of t is equal to rectangle t over tau. Tau in this case, it shows the duration of the this rectangle signal is from minus tau over 2 to plus tau over 2. So the total duration is equal to tau, which is the denominator in this function. So the question is, can you find the Fourier transform of this rectangular signal? So you guys know what to do, is just to use the definition of the Fourier transform to find out the result. And let's remember again, Fourier transform f of w was equal to from minus infinity to infinity f of t times exponential minus j omega t dt. So what we're going to do is to replace this f of t with the rectangle t over tau times exponential minus j omega t minus j omega t dt. Okay, so as you see from the shape of this rectangular signal is there are three regions, right? First region is from minus infinity to minus tau over 2, which is equal to 0. And from minus tau over 2 to plus tau over 2 is this signal is equal to 1. And for the third region is from tau over 2 to the infinity is 0. That's why in order to evaluate this integration, so we split this integration in three parts. The first one that I mentioned is from minus infinity to minus tau over 2, and the value is equal to 0 times exponential minus j omega t dt, plus the second region, which is non-zero, from minus tau over 2 to tau over 2, and the value in this case is 1 times exponential minus j omega t dt. And the third region is from tau over 2 to infinity, which has a 0 value, times exponential minus j omega t dt. So this, the first and second, the third term is equal to 0 because of this 0. And only remaining term is this middle one, the second region, which is from minus tau over 2 to tau over 2 exponential j omega t dt. Now you guys know how to evaluate, solve integration that consists of exponential signal, which is equal to 1 over minus j omega times exponential minus j omega t. And the lower limit is from minus tau over 2, and the upper limit is from up to tau over 2. So if you evaluate this result for these limits, we're going to end up with 1 over minus j omega times 1 over 2 times exponential j omega tau 2 minus a exponential plus j omega tau over 2. And here I add, I multiply this result with 2 and divide by 2. So it doesn't change the result, right? Because they cancel each other. So I multiply with 2 and divide by 2. And the reason for that is because there's a new function, because I'm trying to make this like a sine function. Remember, sine of x is equal to 1 over j2 times a exponential jx minus exponential minus jx. So this looks like a sine function, which is going to be equal to minus sine w tau over 2. So the result is we have 2 times sine w tau over 2 over over w. Then there's another function which is called sinc function. I don't know, have you guys heard about sinc function? Sinc of x is equal to sine of x over x. So if I want to make this like a sinc function, what is missing is the tau over 2. That's why I multiply this result with tau over 2 and divide by tau over 2. Again, it's not going to change it's not going to change this result. My intention here is try to make this signal looks like a sinc function. So after all these operations, the final result is going to be tau times sinc function, sinc of w tau over 2. As a result, so our signal was, remember guys, it was a rectangular signal, which is a duration of tau in time domain. If I apply the Fourier transform to this signal, I'm going to end up with tau times sinc function, w tau over 2. If you want to draw the sinc function, it looks like this. It has a main lobe, like with the value of tau at 0. And then we have a side lobes that, you know, faded as you go to infinity. So it approaches to 0 as you increase the frequency. So the main lobe is very high, and the side lobes on the right and the left hand, they faded as you increase the frequency. So this how it looks like in frequency domain. This function have a lot of application that you guys are gonna learn later on, maybe in your master PhD study. So, but this is one of the popular signal or function that we use in many engineering systems. Okay, that's second example. Let's have another example. So this example set is asking for a signal f of t that is equal to delta of t in time domain, delta or impulse signal. And the question is, can you find the Fourier transform of this signal, which is f of w? Remember, delta function in time domain, it looks like this. It has a non-zero value only at t equal to 0. So at t equal to 0, this function, this signal is equal to 1. For the remaining t values is equal to 0. Okay, let's solve it together. And again, we're going to use our definition that we just learned. F of w is equal to, from minus infinity to infinity, f of t times exponential minus j omega t dt. So what I'm going to do is similar to the previous example that we have done, is just plug in the f of t into the respective place, which is delta of t times exponential minus j omega t dt. How we evaluate this integration that consists of delta function, because it has only value at t equal to 0, which is equal to 1, and then you put t equal to 0, this exponential 0 is also 1. So the result is 1 times 1 and is equal to 1. So as a result, if I have a such delta function in time domain, the Fourier transform of such signal is equal to 1 for all the value of w. Visually, it looks like this. That is the delta function in time domain. And if you apply the Fourier transform to this signal, which is going to be equal to 1 for all the frequency value, which is w. So how do we interpret this result? One interpretation is that, so as information or the energy in time domain is only focused on t equal to 0, but when you apply the Fourier transform to this information or this signal, you spread, or as if you are zoom in the frequency domain. As you see, it's spread all over from minus infinity to infinity. So that's, actually one of the main idea behind using the transform. Sometimes the information or the signal in time domain is very hidden or just focused on one point. And when you apply a Fourier transform or other type of transform, you spread this information or zoom into this information so that you can see more details. Any questions so far? Okay. Let's have another example. Now, this example is for the inverse Fourier transform. So let's have an example for the inverse Fourier transform. Now is a kind of opposite example. In this case, we have an f of w, which is delta function in frequency domain. Now, the question is, can you find out the inverse Fourier transform of this delta function in time domain? So, similar to the forward Fourier transform, in the inverse Fourier transform, we're going to use the definition. And definition says that f of t is equal to 1 over 2 pi from minus infinity to infinity f of w times exponential j omega t dw. Remember, guys, one of the main difference was this exponential was minus in case of forward, but in the inverse Fourier transform is the plus. Anyway, so let's continue to solve this transformation, which is equal to 1 over 2 pi from minus infinity to infinity. So just plug in the FW, which is equal to delta of W times exponential j omega t dw. Similar to the previous example, how we're going to solve this integration, because it has only value at w equal to 0. We just evaluate for this value, because for the remaining value is equal to 0. So at w equal to 0, w delta function is equal to 1. And if you put the w in the exponential as 0, exponential 0 is also 1. So the result is 1. But we have a constant at the beginning of at the front of the integration. That's why the result is 1 over 2 pi. But conventionally, we don't show as a 1 over 2 pi because of this can be a kind of a ratio. So we can move this 2 pi to other side. So the result in the table that you're going to see also in the table is equal to 2 pi delta omega has an inverse Fourier transform, which is equal to 1. So how it looks like in visually, remember that was the delta or impulse function in frequency domain. And similar to the previous example, the inverse Fourier transform of this signal is equal to 1 for all the value of t times. Okay, that's another example for inverse Fourier transform. Any questions so far? Okay. Another example, one of the popular signal, which is cosine. Let's say f of t is equal to cosine w0 t. The question is, can you find the Fourier transform of this cosine signal? And if you draw the cosine, you remember guys, it looks like this. It has a maximum value of 1 at t equal to 0. So, depend on the signal, we may have different approach to solve this equation problem. So the first approach so far that we use is just use the definition, which was f of w was equal to from minus infinity to infinity f of t exponential minus j omega t dt. But sometimes it's a tedious task to this to use this integration because it can be really messy. So the second approach is to use some properties of the Fourier transform that we're going to learn. Remember, we just previously learned that in the time domain 1 has a corresponding Fourier transform of 2 pi times w, delta w, sorry. We're going to learn a property that if you multiply a signal with exponential minus j omega 0 t, is going to be a shift in the frequency domain. Similarly, if you multiply this with the positive j omega 0 t, it's going to be w minus w0 in the frequency domain. Why we use this property? If you add them up, it's going to be exponential minus j omega 0 t plus exponential minus j omega 0 t. So because the cosine was equal to 1 over 2 times exponential jx plus exponential minus jx. So we are trying to make this form. That's why we use this property of the Fourier transform to solve easily this question. So I add them up, but what's missing is 1 over 2. That's why I multiply both sides with the 1 over 2. I add them up, the right hand side also, which is equal to 2 pi times delta omega plus omega 0 plus delta omega minus omega 0. So to make like a cosine, what's missing is 1 over 2. That's why I multiply both left and right hand side with 1 over 2. And these guys, they're going to cancel each other. The left hand side is going to be equal to cosine omega 0 t, which is my signal that I'm looking for. And the Fourier transform of that is going to be pi times delta omega plus omega 0 plus delta omega minus omega 0. So that's how we use the second approach to solve such question. Believe me, if you try this f of t with this using the first approach, you just plug in the cosine and you're going to see it's going to be really messy integration that you need to solve it. So this approach that use the property of the Fourier transform is much easier than the first approach. So it depends on the complexity of the signal. So you decide, depend on the complexity of the signal, which approach to use. Okay, see, as I mentioned, we have done many kind of example to show you the Fourier transform of different signals. Similar to the previous, like Laplace and Z transform, we have the Fourier transform table that shows these pairs in that table. So you can look at the table 7.1 in your textbook for this table. Okay, so we have what we covered so far was to introduce the forward Fourier transform equation, as well as the reverse operation, which is the inverse Fourier transform. After this introduction, we give some example for the forward Fourier transform, and then we give an example for the inverse Fourier transform as well. And then we show another example how to use the property of the Fourier transform to solve some equation, some problem. So you don't necessarily always have to use this approach. So sometimes you're going to use the property of the Fourier transform to solve the problem easily. Okay. Any question? Okay, let's have a 15 minutes break. So we'll continue at 2:30. Okay, guys, we are back. Can you hear me now?
Yes.
Okay, so in the first lecture, we learned the Fourier transform and the inverse Fourier transform, and we solved some examples for these two forward as well as the inverse Fourier transform. Now, in this lecture, we're going to move on to the property of the Fourier transform. That is very useful when you solve the equation problem in practice. So let's start with the first property, which we call duality property. Let me explain in this way. So assume that we have a time domain signal again, f of t, with the lowercase f of t. Remember, according to the definition, the corresponding Fourier transform we denote by uppercase f. So f of w. If f of t has a Fourier transform of f of w, then we can change this function, as you see, from capital F with the lowercase f, and the result is going to be this way. So capital f of t is going to have a Fourier transform of 2 pi lowercase of f of minus w. It has some application. Let's give an example for this. Remember, we did an example for the rectangular signal. F of t is equal to rectangular t over tau, and the tau was, remember guys, it was the duration of the signal, and we solved together, and we found that the Fourier transform of this f of w is equal to tau times sinc omega tau over 2. So let's apply this duality property to these pairs. So the capital F of t is going to be equal to tau times sinc. So I'm going to replace the w with the t times tau over 2. And this signal is going to have a Fourier transform of 2 pi times lowercase f of minus w. So you just, if you know this property, you can just easily solve this problem, as you see. Otherwise, you have to go through many integration to solve this problem. Visually, it looks like this. In the first case, f of t was equal to rectangular tau over t over tau, which is a duration of tau, and the Fourier transform of this was sinc function, which looks like this. If I apply this duality property, then capital of f of t is gonna be tau times sinc t times tau over 2, which is a sinc function in the time domain. It's gonna have a Fourier transform of rectangular times 2 pi in the frequency domain. So that's the first property. The second property is called scaling property. Assume that we have a signal in time domain, which is f of t, and the corresponding Fourier transform is f of w. Then for any real constant a, if I scale this signal by a, means f of a times t, the effect of this scaling in time is going to be two effects in the frequency. One of them is multiplication with 1 over absolute value of a times f of w over a. So the scaling is going to have such effect. Let's give an example. Same example as previous property. So our signal is f of this is a rectangular signal in time domain. And you guys know that has a Fourier transform as a sinc function in frequency domain. So let's scale this rectangular signal by 2, which means that I'm increasing the duration from tau to 2 tau. I spread this signal in time domain. What's gonna the effect of this spreading in time? Is gonna be compression in frequency domain. So if you spread a signal, scale a signal, spread a signal in time domain, the corresponding effect is gonna be compression in frequency domain. So we spread by factor of 2 in time domain, and our signal in frequency domain is compressed by factor of 2. So this is the scaling property. Another property is called time shifting, which we saw in many transforms. We have the similar property in the Fourier transform as well. Again, if f of t has a corresponding Fourier transform of f of w, then I shift this signal by amount of t0 in time domain. In other words, ft minus t0. The effect of this time shift is going to be a phase shift in frequency domain, which you're going to multiply the original signal f of w with the exponential j minus j omega t0. So this property is called time shifting. So let's have an example for this. The question is, I have a signal f of t in time, which is equal to exponential minus absolute t minus t0. And the question is, can you find the Fourier transform of this signal? Now, the first approach you can use the integration by definition to solve this equation. Or the second more easier way is to use this property using the table 7.1. So according to table 7.1, let me show you also this table. You guys might see this table. Can you see the table, please, guys?
Yes, I can.
Okay, so look at it. So this shows the Fourier transform pairs. So what we are looking is this exponential minus absolute t has a Fourier transform of 2 alpha over alpha square plus w square. So we're going to use this property. Let me go back to our lecture notes. You see now, right? Okay. So using the property that I just show you in the table 7.1, according to this table, exponential minus a absolute t has a Fourier transform of 2a over a square plus w square. So if I'm gonna use this property, actually, our signal is the shifted version of this signal, right? By amount of t0. Then what I'm gonna do is just multiply this result with the exponential minus j omega t0. Then I found the result easily, which is equal to 2a over a squared plus w squared times exponential minus j omega t0. This is how you solve a given question easily using the property as well as the table. Another property is called frequency shifting. Is an opposite of the previous property. Now, in this case, we are going to shift the signal in frequency domain. If f of t has a corresponding fw of Fourier transform, then if I shift this f of w with the amount of w0 frequency, the effect of this shift in the frequency is going to be multiplication of exponential in time domain with the signal. So the result is going to be f of t times exponential j omega t0. Okay, this property can be used in many places, and I'm going to just show you one of application. You guys know AM modulation in radio, that you listen the radio, the music in your cars. So it uses an amplitude modulation, AM modulation. And amplitude modulation is based on this property. So f of t is your music in base station, in the radio station A or B, or whatever you call radio A, radio B, radio C. I'm not going to give you a specific name for a radio. So if you want to play this music f of t and you want to broadcast to your audience, to the cars and the people to listen, you just multiply with the cosine omega 0 t. Omega 0 in this case is the frequency of your radio station, like 91.4 megahertz or 93.4 and 100.8. You search for the radio to listen music. This W0 is that frequency that you are searching. So f of t is your music, and W cosine W0t is your station frequency, radio station frequency. So what this radio station have a transmitter. So transmitter multiply this music with this cosine, this frequency. Remember the cosine x was equal to 1 over 2 times exponential jx plus exponential minus jx. So if I apply this, f of t times cosine omega 0 t is going to be equal to 1 over 2 f of t times exponential j omega 0 t plus f of t times exponential minus j omega 0 t. So according to this definition, multiplication of f of t with the exponential correspond to the shift in the frequency. So the Fourier transform of this is going to be f w minus w0. The Fourier transform of this part is going to be equal to f of w plus w0. So this W0, as I mentioned, is a channel frequency. Radio channel is 85.2, B channel is 97.5, and so on. You see, this property is very simple, but it's one of the, most common property that we use in practice using the radio station. Another property is called convolution. Remember, we use the convolution for the zero state response, right? To find the zero state response. In time domain, assume that we have f1 of t and the corresponding Fourier transform is f1 of w. Similarly, we have second signal f2 of t, and the corresponding Fourier transform is f2 of w. Then the time convolution is, if you convolve these two signals in time domain, which is f1 of t convolution with f2 of t, this operation corresponds to the multiplication of f1 of w with f2 of w in frequency domain. So instead of convolving these two signals, which is gonna involve to some integration, instead of that, you can multiply, simply multiply these two signals to find out the result. Similarly, the frequency convolution, if you convolve these two signals in frequency domain, and the inverse Fourier transform of this correspond to the multiplication of f1 of t with f2 of t. We're gonna use this property later on to find a zero state response using the Fourier transform. Another property is called time differentiation and time integration. Let's start with the differentiation. If f of t has a Fourier transform of fw, then the time differentiation with the differential of f of t with respect to dt. So if you take a derivative of a f of t, this is gonna correspond to the multiplication of j omega with the f of w. So if you take a Fourier derivative of a signal, you multiply that with original signal in frequency domain. And this for the first derivative. If you do second derivative, it's gonna be squared. Third derivative is gonna be third j omega power of 3 and so on. Let's look at the time integration. If you take the integration of this signal in time, you're gonna divide original signal by j omega and plus some initial condition, which is pi times f of 0 times delta of omega. Okay, so these are important when we perform an LTIC system analysis, which is the next topic and the last topic. So linear time invariant continuous system analysis, we're going to use the Fourier transform to analyze such LTIC system. Remember that LTI system was represented by the polynomial QFD times y of t, which is output signal, is equal to P of d times f of t. So input is f of t, output is y of t, h of t is our signal impulse response. In this case, we're going to replace the d with the j omega for the Fourier transform. So remember from the previous differentiation property, if you take the derivative of a signal, which is dk times y of t, means that you take the differential of y of t with respect to t, k times. This corresponds to the j omega of k times y of omega. So if I replace this polynomial by replacing the d with the j omega, my new polynomial is going to be q of j omega times y of omega is equal to p of j omega times f of omega. And remember from the convolution property, the zero state response y of t is equal to h of t time, convolution with the f of t. This corresponds to the y of omega is equal to multiplication of h of omega, which is the system transfer function, times f of omega, which is the input function. So instead of convolution, we're going to use the multiplication in frequency domain. In this case, h of omega is equal to y of omega over f of omega, which correspond to the p of j omega over q of j omega. And sometimes we may, guys, give you Laplace form, which is h of s. So how you're going to convert the h of s to the Fourier transform is just replace the s with the j omega. Remember, in the previous lecture, we said that there's a connection between the Laplace transform and the Fourier transform. So the Fourier transform is a special case of Laplace transform when s is equal to j omega. In other words, the sigma is equal to 0. Okay. The last example for today, to use the Fourier transform in order to find the zero state response of the following LTIC system. So the question is in terms of the Laplace, h of s, which is equal to 1 over s plus 2. And the input is given in the time domain, which is exponential minus t times u of t, unit step function. Visually, it looks like this. My system transfer function is given in terms of Laplace in terms of s, which is equal to 1 over s over 1 over s plus 2, and the input signal in time domain. So the question is, can you find the zero state response of this system? So I'm gonna convert all these different, signal into W form, which is to utilize the Fourier transform. So according to the Fourier transform, the zero state response y of W is equal to h of W times f of W. But the question is, we need to find out the h of W and f of W, right? Which are unknown. So f of t was given to be my exponential minus t times u of t. If I take the Fourier transform of this, is equal to f of W is equal to 1 over j omega plus 1. How did I get this? Is I get this from Fourier transform table, which is table 7.1 in your textbook. Okay, so we obtained the Fourier transform of our input signal. Now I need to obtain the h of omega, but I'm given h of s. So I need to convert h of s to the h of omega by replacing s with the j omega. So if I replace 1 over s plus 2 when the s is equal to j omega, and the result is going to be 1 over j omega plus 2. Okay, I completed the first step to find the h of omega and f of omega. Now I'm ready to multiply to obtain the zero state response, which is equal to y of omega is equal to 1 over j omega plus 2 times 1 over j omega plus 1. And you guys know from the previous transforms such as z and Laplace, we use the partial fraction expansion to determine this a and b. So, and if you apply this PFE, you're going to see that a is going to be equal to 1, b is going to be equal to minus 1. So my result ended up with 1 over j omega plus 1 minus 1 over j omega plus 2. Again, if you use the table 7.1, which is Fourier transform table, the inverse of this signal is going to be exponential minus t minus exponential minus 2t times u of t. This is how you find zero state response using the Fourier transform. Okay, guys, so that's all about Fourier transform. Any question? So when we don't use electronic pen, we go faster, right?
It's so harder to for us.
Okay, let me order a new pen so for the upcoming lectures. Okay, that's it for today. I guess you guys don't have any question. Okay, once again, so next week is official holiday, is Eid. So Ramazan bayramı çarşamba öğleden sonra Arefe olduğu için resmi tatil. It's an official holiday. That's why we are not going to have a lecture. So I'll see you after the Eid. Bayramdan sonra inşallah görüşürüz. Şimdiden bayramımızı tebrik ediyorum. So Eid Mubarak in English and bayramınız mübarek olsun.
Sizin de hocam.
İyi bayramlar hocam.
İyi bayramlar. Kendinize iyi bakın arkadaşlar.
İyi bayramlar hocam.
İyi bayramlar.